Welcome to Lecture 12 for Chemistry 141. We're going to finish up our ventures in Chapter 4 and get started on Chapter 5 in this lecture. So the last couple things that we want to wrap up in Chapter 4, one of which is trends in ionization energy. Now, ionization energy is the energy that is required to remove an electron from an atom or an ion that is in the gaseous state. And very often we're reporting either the first ionization energy, which is the energy needed to take an electron away from an atom, or the second ionization energy, which is the energy needed to take a second electron away from the ion that was formed during the first ionization. So if we look at something like sodium, we have our first ionization energy there. So we have sodium in a gaseous state, and we're taking an electron away, forming Na plus an electron. And we see it has a positive ionization energy, which would make sense. We should need to put energy in to remove an electron from a sodium atom, because it's going to have, you're trying to remove something negative that's attached to something that's positive. And then we have our second ionization energy, and we see that it's much greater in energy, almost by a factor of 10, where we have Na plus going to Na2 plus another electron. Now we can look at the trends there as we go across the periodic table. We'll look at first ionization energies here initially, and we see that ionization energy generally increases as we go across a period. So here, as we go from lithium up to neon, we increase in ionization energy. As we go from sodium to argon, an increase. Potassium to krypton, a general increase. We do have some issues there with the transition elements. If we take a look at groups, as we go down a group, this makes it a little easier to see. We can see as we go from hydrogen down to cesium, ionization energy goes down, beryllium to barium, ionization energy goes down, etc. And we see that trend through all of our groups there. Now we see some little hiccups in here with right there, right there, right there, and right there. And the reason for that is at that point we're getting to either full shells or half shells. As we go from lithium to beryllium, right here, we've now filled our shell, and so as we try to remove an additional electron, it gets harder and harder to do. So the ionization energy there for beryllium is a little bit harder than expected, because we're removing an electron from a filled S subshell, and then it goes back down as we move on to onto boron. And then we come up here to nitrogen, and there nitrogen is a little bit higher than anticipated, and the reason is because we've got a filled half shell there and really don't want to remove an electron from it. And as it turns out, the energy for carbon is a little bit lower than expected also, and this is because the removing of that fourth electron will give us a half-filled p subshell there, and so the energy is a little more favorable because it likes getting to that half-filled subshell. So little burps here and there as you go through, but we're really worried about that general increase as we go across a period, and a general increase as we go down a group. Now, if we start looking at second ionization energies and above, we really have no specific trends that we can report, mainly because it's really dependent upon where that atom lies in the electron configuration, where the ionization is in that atom's electron configuration. And the real issue comes in, are we trying to take out valence electrons, or are we trying to take out core electrons? And if we're trying to remove a valence electron, it's going to be much easier than trying to remove a core electron. Let's compare sodium and magnesium here. So we see with sodium, removing that first electron is relatively much easier than trying to remove that second electron. And this is because our first electron in sodium is a valence electron. That second electron is a core electron, and it really doesn't want to go. If we look at magnesium, magnesium has two valence electrons, and so removing that first electron isn't too bad. Removing the second electron is a little bit harder, but it's still a valence electron. But then compared to trying to remove that third electron here, the third electron now is a core electron, and it's much, much harder than it was to remove either of the valence electrons. So the second ionization energies and above really depends on whether or not we're removing a valence electron or a core electron. We can really sum this up in a table where we see as we go down, or across rather, a period here, going from sodium to magnesium to aluminum to silicon there, we're increasing the number of valence electrons, and we see that we have one valence electron here before we start getting into the core. In group 2, we've got 2 valence electrons before we start getting into the core. For group 3, for aluminum, we've got 3 valence electrons to remove before we start to get into the core. And you can really see a large jump between valence and core electrons in the energies needed. So just something to look at. One concept that our book brings up is something called electron affinity, and this is the energy change involved in adding an electron to an atom. Missing a word there. So adding an electron to an atom. Generally, this is an exothermic process, mainly due to the plus-minus attraction between electron and nucleus, but occasionally it is endothermic, depending on what else is going on in the atom. Are you trying to pair electrons up? Because that's energy that's going to be working against that exothermic process. So there's always a balance between endothermic and exothermic processes there. Let's take a look at one that's favorable, and that's chlorine gas plus an electron going to chlorine minus, the chloride ion there. And we see the electron affinity there is negative 349 kilojoules per mole. And this is something we might expect if we look at the electron configuration for chlorine, a chlorine atom. It's going to be 3s2, 3p5, and the gain of that one electron is going to make it a 3p6, and so that's going to give it a filled outer shell that's going to give it the same electron configuration as noble gas argon, and that's going to greatly stabilize that chloride ion. And so it's going to, we would expect that that process would be fairly exothermic. The trends here with the electron affinity, some of them are regular, some are not. There's a lot of complicating factors in looking at the trends of electron affinity, so it's not going to be something that we're going to delve into too deeply. All right, well, that finishes out Chapter 4, and we're going to get started in now on Chapter 5, really starting to look at chemical bonds and how we're going from atoms now moving up to molecules. It's the next logical step in an atoms first pedagogy. Now, chemical bonds, if we take a look at that, most things, what we see with chemical bonds is that most things that we do in chemistry, the reasons why things happen, why reactions happen, why things bond together, are pretty much always about energy. And any time that we're raising the energy of a system, we're reducing its stability. And conversely, when we lower energy, we are generally increasing stability. Now, chemical bonds form usually because the resulting species after atoms have bonded, that resulting species has a lower energy than what the original atoms had individually. Now we've got a couple of main types of bonds that we're going to look at. We have ionic bonds and we have covalent bonds. Let's take a look at each one of those separately. Our ionic bonds involve a transfer of an electron, sometimes more than one electron, from one atom to another. Usually from a metal to a nonmetal. So we're moving electrons from a metal that tend to lose electrons to nonmetals which tend to gain electrons. When we transfer one or more electrons, those atoms are going to gain opposite charges. So the atom that loses electrons is going to gain a positive charge, and the atom that gains electrons are going to have a negative charge. Well, now we've got a plus and negative charged ions that are next to each other. So we have a cation and an anion, and they are attracted to each other through that electrostatic attraction, or through Coulomb's law. And this is what we call an ionic bond, that plus minus electrostatic attraction. Now, if we have lots of cations and anions together, which we usually do, they're going to hold together in a three-dimensional lattice. It's not just a single cation and a single anion that are attracted to each other. Any cation is attracted to any other anion in the vicinity, and any anion is attracted to any cation in the vicinity. And so when we're making these compounds, we end up with these three-dimensional lattices, and this is what we call ionic compounds. We can take a look at a graphic for what this is going to look like here. And so here we've got our sodium metal with 11 electrons, one valence electron. It loses that one valence electron going over here to the chloride ion, or to the chlorine atom that has 17 electrons and 7 valence electrons. When the sodium loses that one electron, it becomes a sodium ion here. Now has a plus charge. Our chloride ion now has 8 electrons and a negative charge. So put a little minus there, and we now have an attraction between the sodium ion and the chloride ion. And again, any sodium ion in the vicinity is going to have an attraction to any chloride ion that's nearby, and the chloride ion is going to have an attraction to any sodium ion nearby. And so when we have a large sample of sodium metal and chlorine gas, we're going to have lots of sodium ions forming and lots of chloride ions forming, and as a result we get this three-dimensional lattice with an alternating pattern of sodium ions and chloride ions as we go through there. And we see that as sodium chloride crystals, and also called table salt. Covalent bonds are somewhat different from ionic bonds because rather than a transfer of electrons, instead we're seeing a sharing of electrons. And these generally form between two nonmetals, as opposed to ionic bonds, which form between metals and nonmetals. So the compounds that form with covalent bonds we call molecular compounds, and they are individual, discrete molecules. They're not these three-dimensional lattices that we see with the ionic bonds. When we're looking at chemical formulas, all we're doing is indicating the elements in the compound and the relative numbers. So we can look at something like H2O, which is molecular, and this tells me I have 2 hydrogens and 1 oxygen atom there. Notice that we don't write a 1 down here next to the oxygen. That's understood if we just have the oxygen there. We have sodium chloride, which is ionic. Now this is more appropriately called a formula unit, and instead of just saying that I have 1 sodium ion and 1 chloride ion in a sodium chloride molecule, we don't really have molecules there because we have that three-dimensional lattice. So this gives us a relative ratio saying I have, for every 1 sodium ion I have 1 chloride ion. So it has a 1-to-1 ratio within that three-dimensional lattice. I have magnesium fluoride there, MgF2, saying I have 1 magnesium ion and 2 fluoride ions, and that is also ionic. And this gives me again that relative ratio. For every 1 magnesium ion, I have 2 fluoride ions in that lattice. And then my last one there is molecular. Notice we have 2 nonmetals, carbon and chlorine, and this tells me I have 1 carbon and 4 chlorine atoms in that molecule. So let's take a look at empirical formulas, and these are formulas that just give a relative number of atoms of each element in a compound, and a lot of times you just get these by certain types of analyses. So if we look at something like H2O2, hydrogen peroxide, some analyses would just give us that we have a 1-to-1 ratio of hydrogen and oxygen, and that's as much as it could tell us. And then we have molecular formulas, And molecular formulas give us an actual number of atoms of each element in a compound. So they give the true chemical formula for a particular compound, telling us exactly how many number of atoms are going to be in a molecule of that compound. Then we have structural formulas. And structural formulas show us not only the number of atoms that are in a particular molecule, but also how those atoms are attached to each other. And sometimes they may indicate geometry, and sometimes they may not. So here's an example that does not show geometry here on the left. So this again is our hydrogen peroxide, but it does show us that we've got a hydrogen connected to an oxygen, which is connected to another oxygen, which is connected to hydrogen. However, there is an angle associated between the oxygen-hydrogen bonds there, and so we've got our bond right here, and our bond angle right here, and another bond angle right there. And so the only time we ever use this type of formula is with molecular compounds. We don't generally draw out our three-dimensional lattices that we see with our ionic compounds. Now when we're showing our molecules, we have different ways of displaying our models here. We have a structural formula here on the far left, so CH4, or rather molecular formula. We've got our structural formula here in the middle there, where we're showing the bonds and how they're attached. We've got our ball and stick model, where we're showing the individual bonds and the atoms as spheres on there, and we do get some perspective as far as how things are connected. We can see the actual angles involved in the general shape of the molecule. One thing we want to make sure we don't get from that ball and stick model is that there's this huge gap between the atoms with this line making a bond between the atoms, because that's not really how atoms come together. The space-filling model is really a more accurate portrayal of what a molecule would actually look like, where you have atoms actually kind of smushed into each other. Their electron clouds have overlapped and combined to form the bonds. However, it's not as easy to see the molecule using the space-filling model. So if we want a good three-dimensional view, more often than not, we'll see the ball and stick model. Let's take a look at Lewis structures. This is one of the ways that we can represent ions in atoms using just dots as electrons. And so what we do is we count up the number of valence electrons for an individual ion or atom, and we add the valence electrons singly for the first four. So we kind of put them at the 12, 3, 6, and 9 o'clock positions around a chemical symbol. And then if we have more electrons to add after those first four, then we can start to double up. So if we look at oxygen as an example here, we've got 6 valence electrons. It's got an electron configuration of 1s2, 2s2, 2p4. So we see those 6 valence electrons. We also could have got that 6 valence electrons by looking at the periodic table, seeing that oxygen is in group 6, and that tells us that we have 6 valence electrons. If we look at the electron dot structure for oxygen, it's going to look something like this. So we would put a dot here, here 2, here 3, here 4, and now I've got 2 electrons left, and so now I can start pairing them up. And so we'll take a look at that in class as well. Here are some examples for dot structures that we'll work out in class, but we'll look at sodium, look at fluorine, look at phosphorus, and look at neon. Now, in using those dot structures, we can use them to help us predict how atoms will bond in a compound, or at least how many bonds it will form in a compound. And so remember that atoms want to look like the noble gases, and we saw in that previous example, once we get through those examples, that neon has 8 valence electrons, as do all of the noble gases. And well, that finishes out the material for that's a term we'll use quite a bit, that atoms try to get this informational in. And as always, if you have any questions, make sure you contact us. So we can use that dot structure of the atom to predict the number of electrons it will gain or lose in forming a compound. Well, that finishes out the material for lecture 12. Hopefully you found this informational, and as always, if you have any questions, make sure you contact us.